Alright, so we're gonna take all the code I wrote, and we're going to hope that we didn't make any mistakes. I think we'll describe what I'm actually doing in this function, and I'll use that as a visual debugging session to make sure that I have this correct. So I'm going to explain every single thing in this function. So right here, we're going to define this underscore zero underscore as 0, and also underscore is also going to be defined as 0. Originally, I wanted like 3 underscores in a row, but I realized that 2 underscores in a row are reserved for future constants in GLSL, so we can't do 3 underscores in a row. We can't even do 2. So this define here it should be undefined at the end of the code. And not only should it be undefined, but there shouldn't be any excess tokens after the undef. So if we go all the way down here, we see that indeed we are undefining the underscore 0 and that underscore. So that looks good to me. So going back up to this, we might as well check that these braces are closed. So the braces for this function, they look all right. Okay. So this RWC and RWN, when it's all capital, that is the actual struct name. And this RWC and RWN is the actual data that we're trying to get from this function. So this function reads fragment percentage converted to array world coordinate and array world normal. So together with the coordinate and the normal, we have everything we need for a view array that corresponds to a given pixel on the screen. So you could think of this as a camera array. I don't know what you want to think of it as, but this is our array for marching into the scene and rendering it. So v2 is for a vec2, so if you want to look where that's defined, we can go all the way up to the top of the code, and we can see that we have a list of defines that we use in the entire library, just to keep the code highly normalized, because I'm highly OCD. So float being more than 3 letters, and vec4, vec3, and vec2 also being more than 3 letters. It gets all ugly when you're trying to line up the code. So we normalize this, so all of these defines for these different types are all exactly 3 letters, the way I like things. And going back down to this code, we see that it returns a vector2. Actually, no, this is the input, right? So within here is the parameter list, the open and closing bubble brackets, and this is the fragment percentage that's inputted, and then we're going to output this type, which is array world coordinate and array world normal, all uppercase for the type, and then just kind of like gluing together the variable names within the function name. So originally, I really liked function names to be camel case. However, because I'm just using kind of like abbreviations and the actual literal variable names, it makes a function that I would otherwise want to be camel case into kind of this case. And the reason for that is because now if I select something like array world coordinate and array world normal, if we select that part of the function name, we can actually see the exact variable name that this corresponds to, which just makes it very helpful as far as I'm concerned. So we can see that we're basically going to return this container that is going to store just both of these things. And we're not going to give the container some type of fancy name like iRay or Ray, whatever the hell. We're just going to Lego name it, right? We're just going to name it by exactly what the contents are, because it's just frustrating figuring out names for things, and sometimes I like doing that, but right now I don't want to do that. I want to keep a code convention where I'm just trying to expose what the actual data is, kind of inspired by the data-oriented design lectures I was reading about. Okay, so this is an off-boarded comment. I can tell because there's hashtags around it. Comments are the last thing you'll read when everything else goes wrong, so that's kind of why it's off-boarded, because comments start to take up a lot of space, especially this comment here, this big diagram here. So could possibly use these as slice planes, but for now, using these to navigate our voxel map bounds. Okay, so let's take this is the opening comment, and do we have a closing comment to match? And it looks like we do. Okay, that looks good. We want to make sure that our comment character is as a /**, not a //* or a *//, which I sometimes screw up. Okay, so A, B, C, and D are directly above E, F, G, and H. And the reasoning for that is we just want to make it very easy to mentally wrap our head around, right? So if we highlight all these in our diagram, we should see the corresponding letters in the correct places. So we say that A is cyan and E is cyan, C and G are yellow, and B and F orange, D and H, they are purple. So everything looks like it is in the correct spot for the diagram. This right here is the underside of the cube, and this is the top side of the cube. So we're wrapping a, we're kind of like creating all the vertices for a cube that surrounds the voxel map bounds. And we're going to do that just so that we can have enough variables to work with to figure out how our camera needs to be moved in space. We really don't, we have more variables than we actually need for the calculations we're doing, but I decided we should just get all the variables so I can kind of easily visualize what's going on, and then we could whittle down those variables later. So eventually, this point D right here, I want a camera that is going to tangent point D and give me an orthographic isometric view of whatever geometry is drawn within this voxel map volume. And to do that, we're going to have to figure out how to like rotate a plane and stick it right onto point D. So the middle of the plane will intersect with point D, and we'll use that to render an orthographic view of whatever we're working on. So with that, let's keep on scrolling down. So everything so far looks okay to me because we got these opening and closing comments. We don't have any other things that would terminate the comment inside. These are glued together. Okay, that looks good. So dimensions of voxel volume. So mx, my, and mz stand for max x, max y, and max z respectively. They're float 32 types. We take the number of pixels, the tile pixels x, tile pixels y, and tile pixels z. And these are really actually the total number of pixels. So if we go back up to the top of the file again, and we look at where these are defined, we see that total number of pixels in entire voxel map, ntx, number of tiles, multiplied by the number of pixels within one of those tiles. So when I say tile, I actually mean voxel, but we're going to use a tile map analogy and just extend it, right? So we're just going to take normal tile map math, and we're just going to plug another axis onto it. And with that type of math, we are also going to have our native coordinate space be in terms of fragment coordinates rather than in terms of normalized device coordinates, so that everything will be really easy, because when we're thinking of our units, we can just think of our units as pixels. Like the fundamental unit of all the math in this file is pixels, okay? Now, obviously, voxels are made up of pixels, so you can also think of some math at a higher level using voxels rather than pixels, but the fundamental unit, or like Planck unit, or unit de Franca, whatever you want to call it, it is pixels. So keep that in mind when we're doing this math. So, okay, so right here, that looks good. So TPX, TPY, TPZ. We also might want to highlight it one more time just to make sure. Let's make sure those closing braces are where they belong, and that looks correct. Also, remember that it's 1.0 because this is floating point. So, with that, let's go back up to the top and make absolutely sure we have the correct things highlighted. Yep, that looks correct. Okay, so going back here, let's remove that breakpoint, and this is kind of like where we've looked at. So right here we kind of have these A, B, C, D, and E, F, G, H, and you'll be like, well, where is that coming from? And these correspond exactly to the diagram from earlier. Also, let's make sure that we have cyan for the X, orange for Y, and yellow for Z. So cyan, orange, yellow. And if we look at the columns, we have cyan, we have orange, and we have yellow. So we know that we don't have any transposition errors where we accidentally swapped X, Y, or Z. So that looks good to me. Now I do see a little mistake. It's not a mistake that will result in any problems, but this is basically 0 minus 0, but it's just written this way so that I can kind of have this blank spot. So the important stuff I can see, and the non-important stuff I don't need to see. And you'll notice that these columns are exactly the same, and then the only difference between this block and this block is that we've kind of moved on the Z. we have to remember that when we start at 0, 0, all of the voxel volume is beneath that. But it's a little bit, it can be kind of confusing because we're using a, as you go further into the screen, the Z value increases, and that's just to keep the coordinate space kind of normalized for the tile map calculations. Like, we don't want the tiles to exist in positive X, positive Y, but then for some odd reason, the Z tiles exist in the negative Z coordinate space. Like, that would just make things really wonky and very error prone, so we wanted to standardize that as much as possible. So, when you're going down into the screen, this MZ, though this MZ is a positive value, this makes this go down into the screen. So if we want to highlight the variables here and make sure that they are where we think they are again, so we'll highlight these, and then we'll highlight the respective ones. And then we'll kind of scroll back up here, and okay, we didn't diagram it quite like that up here, because for clarity, putting underscores on these kind of breaks up the diagram, so I didn't do that there. But now that we have those highlighted, we can see kind of, well, what variables are we actually going to use from this chunk right here? And if we look at this diagram, we can kind of see that we have these vectors that incorporate point D. So all these vectors are incorporating point D, and it looks like we're trying to get a edge vector. So edge vectors, and the edge vectors are going to be calculated all using point D, because we can see them in purple. Let's make absolutely sure that our comments are closed off. So we're going to do this, and make sure that we have the two different colors. So we have cyan, orange, cyan, orange, cyan, orange, cyan, orange, and looks like we have a problem, right? So, no, that's not a problem. Cyan and orange, cyan and orange, cyan, orange, cyan, orange, cyan, orange, cyan, orange. So that all looks good. So, with that, let's keep on going. Let's look at our diagram and see what we can find as far as bugs go. So, first thing I'm going to do is we'll just take the letter portion of these vector variables, right? We'll just take those, highlight them, and now we can see the corresponding colors in our diagram are highlighted as well. Now, my convention for a vector is when I say DC, I mean a vector going from D to C. And you have to remember that when you're making your vectors, you have to think of it as you have to read it kind of backwards. So this is C going towards D, D going towards C, D going towards B, and H going towards D. So that's kind of why, like, you might notice that CD is kind of like written backwards compared to how I wrote it here. And that's just because I don't want to have to, when I'm reading these variable names, I don't want to have to flip it in my head. I want to just flip it in the calculation. So CD, so C to D, D to C, D to B, and H to D. So that that looks good. So you'll notice that that the D isn't always in the same place, right? And there is a reason for that, and we'll get into that as we kind of look over this code. But let's make sure we understand what C and D is doing. So CD, so C to D is going from here to here, and then D to C is going D to C. Okay, so these are like same edge, but in different directions. And then for D to B, you go D to B, and then we have D to H. No, we have H to D, so H to D. So that's going to be used to kind of create our a little like those are going to be used to create these like normals that are kind of like radiating from here, and help us create some normals that will help us reconstruct a plane that is tangenting this point. So we're going to kind of like use point normal form to rebuild a polygon that is the size of the voxel area. Or actually, no, not the size of the voxel area. We're going to, ooh, wait, hold on. So when we're looking at, okay, well, that's fine. That's fine. So this cube is the size of the voxel volume. That's fine. Now, I think when I did this code and I was doing the point normal form, well, let's make a little save spot right over here. So this is kind of what we've been looking at. We're kind of up to here. So half width, half height, half width. So these variables right here I'm kind of concerned about. So if we look at this, it is our camera right now. The camera that we're mapping to is not the exact size of the screen. It is actually smaller. I just know TPX, TPY, the number of tiles. So this is going to create a camera that is kind of zoomed in, which may or may not be what we want. So what we could do here is we can say let's just add that as a feature, right? So you know, we'll say like define zoomed in camera 2020 1126, I don't know, right? And then we'll just say it's equal to 1, and then we'll do something like this. We'll do like if we'll take this and we will kind of like paste it right there, and we'll say that, you know, if so I would use like a if def, but I don't think from my observations it doesn't look like GLSL has an if def. So we're gonna do like greater than or equal to 1. And if we have like a zoomed in camera, we'll do this calculation here. And else, if zoomed in camera is like less than or equal to 0, then we will do we'll do the other thing. So right now, there we go. So if we take this and what we really wanted was the eye resolution divided by 2 is kind of what we wanted. So eye resolution.x divided by 2, right? Because we want it to map directly to the screen, right? So if we don't want any zooming in at all, then we have to make this camera plane surface exactly the width and height of the screen, of the client area. So resolution.y. So for that, the width is going to be resolution.x divided by 2, the height, iResolution.y divided by 2.0. So we should make absolutely sure that HW and HH are floats, and we see that they are indeed floats, so we should be good there. Let's double check our math here. So that define is good. So let's undef it. So no need to pollute our stuff with, you know, defines all over the place. So we'll undef it, and that way we kind of know that instead of just changing this mistake, we're just going to change it into kind of like a feature. So camera surface smaller than client viewport means zoomed in, right? That's basically what we're doing here. And then over here, if the camera surface exactly same size as client viewport means no zoom, right? That's what that means. Okay, so with that, let's make sure that our comments are correct and that they are terminated in the correct position, so that still looks good. Float HW, that is, yeah, that's correct, and we need a semicolon to terminate that. The define, that define looks correct. And if we look at these, we have semicolons terminating them, semicolons terminating those. We got 2.0 because these are floating point math. F32 is wrapping this because TPX and TPY, they are defines, and the defines are they don't have decimal places, so therefore they're interpreted as integers. So we have to wrap the number of tiles on the number of tile pixels, or the total pixels x and total pixels y on the x and y. We got to wrap those in float32 constructors. Okay, so that looks good. My only reservation now might be that, are we spelling I resolution correctly? So if we look at I resolution and we say match whole word and match case, we should be able to see it in other places as well. And I see it in one spot, which I would have expected to see it in more places, but I had refactored this, so that kind of makes sense. Okay, so now that we have that, let's go back to 600 and kind of look at what we've been doing here. So mx, my, and mz are for max x, max y, and max z. So we see the total number of pixels on the x-axis, y and z, and there's a -1, and that's because when you start at pixel, the first pixel is pixel 0, right? So if your tile map is, let's say you have a bitmap, right, and it's 64 by 64 by 64 pixels, well, the highest pixel index would be 63, 63, 63. If you had a three-dimensional bitmap, I guess. So that makes sense to me. Let's just color code these again, or not. Let's try that again. Okay, and we already described the math for A, B, C, D. That's good. So let's remove that breakpoint. These diagrams looked pretty good to me. And we were kind of going to look at these vectors and make sure that the math for these vectors are correct. So these vectors themselves, the math for this is all right. Like, these vector names describe exactly what those vectors do. So that is good. So now it looks like we need two vectors to rebuild the plane that's going to tangent point D here. Right? We need, the plane has a x and y. A plane does not have 3 dimensions. A plane can exist in 3-dimensional space, but when you're thinking of the surface of the plane, it does not actually exist. It does not actually have 3 dimensions. It only has 2 dimensions, right? So we need to create some type of, I think you would call it a basis vector. We need to create like a new vector that represents a tilted coordinate space that creates this, that will create a plane that is rotated into a isometric perspective for this voxel volume here. So let's take a look at that. So it looks like the x-axis part was the easiest part, so let's read this comment. X-axis vector is pretty easy because the camera x-axis does not move in the z direction. And so let me think about that. Is that true? Yeah, it is true. Now, I'm just kind of visualizing it in my head, so I'm sorry if you can't visualize that. I mean, I'm not a Nikola Tesla here. I can't like visualize very complicated things in my head, but I can kind of visualize that, and I know that the way I want this plane kind of like rotated in space to get that isometric view of this geometry. It's not going to, when you're traversing the x-axis, the z-axis will never change. As you move along the z-axis of our, when you move along the x-axis of our new basis vector, the world space z value will never change. So let's look at that. So we got the top of this A, B, C, D, and we have this vector here. So D, B, and C, D. So DB, so D to B, and then we have C to D. So C to D, right? So we're creating kind of like a vectors that are kind of like going like this, right? So I'll just add some little frills there to help us visualize that. So right, so these are the vectors we have. We have a vector kind of going like this, and then we have a vector going like that. And the reason for that is we want to be very careful about what's positive and what's negative. We don't want to accidentally invert our viewport rectangle, our screen rectangle, whatever you want to call it. We don't want to accidentally flip that. We want to make absolutely sure we got the positives and negatives correct. So these are the directions we need to point in. So it's D to C and D to B, D to B. We don't have to worry if these variables are correct because we've already checked them and they check out. We could do a little double check since we're looking at this diagram. So we can highlight these two colors. We can look at vec CD and we can see it's C then D, D, B, D, then B. So that still looks correct to me, so we can continue. So what we're going to do to get that AX vector is, let's see, is that correct? Because I don't think that's correct. So we have this X, Y. Okay, yeah, so the X and Y, and that'll get a vector that kind of goes into there. But I don't think that's the whole vector we need. Is that the whole vector we need? Let me think about that. I think that's wrong. That would almost be... yeah, so this AX would actually be a AZ as far as I'm concerned. Because we got the X plus the Y, and we just divide by 2, right? So we're getting something in the middle there. So that would actually be a Z, and we have to take it and blend it with one more vector before we get it moving. Yeah, that's okay. Yeah, so that looks like a mistake. In my math, and now I'm kind of concerned, well, am I doing this correctly? Well, let's look at our AY, right? So we have these different vectors. Is AX where is AX reference? No, so AX is like this final vector we're going to use. So AX is definitely incorrect. So this is actually, I think this is more like an AZ because it's like a 45 and it's kind of like, yeah, I would call that, yeah, I would all, yeah, I think this is, I'm not even sure of that, like, it's not even an AZ because it's because since our plane is going to be kind of tilted, that wouldn't even be correct. So let's try to fix this. So we're trying to create this. So this is this is a 45-degree line on XY plane. So that's kind of what this is right here. And we still need to kind of blend this with something else. We need to blend it with something that's going from D upwards, or actually something that's going from if we look at this, we go at HD. So we actually have to blend it with the HD vector. So we can see HD, and we can see in our little diagram for where we're doing the math here that we had considered these. So we just seem to have neglected that in our math. And why did we do that? I'm not sure. I'm kind of worried that I'm making a mistake here. Oh, wait, hold on. D, okay, I see where I'm making the mistake. So, this is CD, right? This is DC. I'm trying to interpolate that as CD. So, hold on. So, we're actually going like... So, CD is actually going like that, right? And if we look at it like that, we're trying to make... a line that that goes kind of like, our goal is to kind of create a line that's going like this, like the 45-degree angle line that's kind of like going like this, right? That's the goal. So, right. The goal is to create this line right here. The goal is this line for x-axis. AX. Okay, so AX, this is the goal. We want this kind of line here. So if we have D to B, and we have C to D, and we split it in half, we'll get this like 45. I didn't, you know, it's not quite drawn like a 45 just because of the nature of, we could try to like make that more 45-ish, you know, we could try to fix that up a bit. It looks ugly as hell, but, you know, at least that's kind of more of a 45. It's more of a 45 angle. This actually would need... Here, let's... Okay, so... That's kind of what we're going for, right? This like 45-degree angle line that's kind of going through point D for AX. So now that we look at that, this normalize was correct, but we don't need that because we already got the normalize up here, divided by 2.0. So this x and this y, I'm just using a define to temporarily rename them as a x and y, so we know kind of like what those stand for. And we see C to D is on the x, and we see D to B is on the y, because we're kind of like looking down onto this voxel volume. So that, yeah, that makes sense. So AX is actually good. I kind of second-guessed myself, but it's better to second-guess yourself than to never double-check in the first place. So let's keep on looking at this. So make sure you undefine the things that you define before you continue. We're inside of a comment section right here. It's kind of confusing to see where are we inside of a comment section, where are we not, because I didn't really color code that. But I do that intentionally so I'm not distracted by changing colors all over the place, right? Okay, y-axis vector is a bit tricky because it moves on all axes, so x, y, and z. If we average vec dc and db to get a 45-degree on the xy plane, we can then tilt that vector up by 45 degrees by averaging it with vec hd. So let's take those colors and let's color them in order. So we're going to do cyan, yellow, and orange, and that's just the order that it is in my shortcuts on my editor, so that's just the order it's going to be. So the first thing is we're going to average DC and DB. So we can actually look at the colors here, and we know that it's the cyan and the orange. So we're going to take this cyan and we're going to take this orange, and we're going to average that together. We kind of see in the diagram that cyan and orange is right here. So we know that D to C, D to B, okay. So we're trying to draw like this 45 that's kind of going towards A. Now it's important that we don't make a vector from D to A, because that math would only work if the voxel volume was exactly a cube. Once it's not exactly a cube, that would no longer work. So we want to think of the sharp corner of here and create our vectors from this corner, and we're not even considering A in this math. So we got this 45-degree line that is on the xy plane. Okay, so that looks good to me. So that first averaging step, that makes sense to me. With the cyan and the orange, and we see that we're calling them x and y, right? Because they're our x vector and our y vector. We're just going to add them together, we're going to average them, and then we'll normalize them to get a new directional vector that is a 45 on the xy plane. Okay, so after we have that 45 on the xy plane, we're going to average it with the z, and z is the vector HD. So you see we have a little tiny diagram right here, but we can go scroll back up and see HD is H to D, and H to D goes from H to D like that. So even though it's down here, we're kind of imagining H and D kind of like up here, hanging above, because we want to like pry this vector kind of like up, right? So the vector that is on the xy plane, we're going to pry it up by blending it with that vector HD that goes H to D. That's going to go like up in kind of like this direction, right? The vector HD is going to go up here, and this other vector is this axis, and then I can't really highlight that, but you get the idea. So with that, for ZHD kind of makes sense to me, and we're normalizing this before we blend it with the other one, so let's make sure our brackets make sense. These brackets make sense. Then we add, and then we close it off. That might not make sense. Oh, it's this, and then, so maybe we want to, do we want to be a little bit more verbose so that that is a little bit more readable? I don't know. We have the space, so we might as well do it. So let's kind of reorganize that a little bit. So these braces match, and we're dividing it all by 2. Normalize plus, so we know we're adding something. Yeah, I mean, I think that works now when we're adding. So this, and then we normalize the whole result. So every time we add and divide, we got to normalize. So we normalize because we've added and divided, and then we take these and we add them and we divide them, and then we normalize again. So that looks correct to me, so we can keep on going from there. So these defines, we have 3 defines, which we also undefine at the end. We don't have any scrap junk on the end of these undefs, so they will compile correctly. Okay, so let's keep on going. So now we're kind of like down here. And what do we have? So we have a big diagram here. We can now use point normal form to build a camera polygon. We will start from point D and walk halfway the width in both directions on our altered x-axis, vector AX, and halfway on the height in both directions in our altered y-axis, vector AY. Height is the height of our camera plane, and width is the width of our camera plane. This is correct. No matter what the define is, so the define for this, if we go all the way up to, we like added a define. Where are you? There's some define, or maybe it's further down. Yeah, this define right here, right? So when we're defining half the camera width and half the camera height, we may have a zoomed-in camera or a non-zoomed-in camera. This is the non-zoomed-in camera because we're going to create a polygon for the camera surface that is exactly the size of the screen surface. And this one is our mistake that we're going to just turn into a feature, which is creating a camera whose size is exactly the width and height of the voxel volume. And when I say width and height, I mean the x and y dimensions of the voxel volume. When I speak of the z-axis, I will usually say depth. So that looks correct to me. Now this diagram I know is, like right here, is incorrect, because we can't just use point normal form to get these points and then kind of like take components and mix and match them to get these vertices here. That will not work because we're using a vector that's kind of like rotated into 3D space to create a new coordinate system, and this would only work in our native coordinate system. So this isn't going to work. I kept it, and I kind of like corrected the comments later, just to know that so I can see my erroneous thinking, kind of a thing. So cam center. In order for the camera to be 100% centered, it may be necessary to squash or stretch the camera by 1 pixel if the camera is not an odd number of pixels on that axis. See diagram. So yeah, so like if we have a camera that's kind of like 3 pixels, then the middle of the camera kind of is perfectly on that pixel at the at one of the edges of our voxel volume, right, point D, and everything is nice, but if we had a camera that instead of 3 pixels, it was 4 pixels, we wouldn't be able to latch the camera directly into the center, right? So we are trying to think of all our math in terms of discrete units, right? Even though we're using floating point, we want to think of everything as pixel coordinates in 3-dimensional space. So that makes sense. Okay, so we have kind of a little diagram describing kind of like what was going on up here. That's fine. Now, this diagram really makes more sense just putting it in here, because that's kind of like what it's all about, right? Now, we got to make absolutely sure we remove these characters, because we cannot have a comment, a multi-line comment within another multi-line comment. That will create us some problems. So, half width and half height. That looks good to me. Okay, so now we're going to take tile pixels X, tile pixels Y, and we're just going to divide those by 2. And then otherwise, if less than or equal to 0, so greater than or equal to 1 or less than or equal to 0. That is decent math, so I don't think we're going to have these uninitialized. So we're just hope that that is correct, because we've read it carefully. Let's look at this. So, to be pixel perfect, floor and seal need to be used. This is an OC optimization that can probably be removed without noticeable difference. So now I realize that this crap here, right, with these, it's in red because that means it's been removed, and I just kind of have it for reference. But if we look at these points, with the positive X, positive Y, negative Y, so that's wrong. So this NZ should not be like that. And in the diagram, it's not a Z. This is a negative Y, positive Y. So that's positive Y. And let's try this over again. So let's color code everything again and make sure that everything is accounted for. And now we see positive X, negative Y, positive Y, I, J, K, and L. So I, J, K, and L are going to be the final vertices of our camera surface. And let's just scroll up and see where else this is highlighted. So this crap here, again, it looks like I still screwed up here. So negative Y, and once again, this is positive Y. So let's highlight those again. So it doesn't really matter what colors we use, just as long as we use some unique colors. Yeah?
Dinner is in about 10 minutes. Frankie's coming down, and it's meat heavy.
Okay. See if I can get through this. Okay. So that looks good there. Let's scroll down, make sure everything is accounted for. Okay, so now the final part is just trying to calculate I, J, K, and L. So let's get rid of the color coding, and let's just do I, J, K, and L. Okay, and let's see, do these colors make sense to us? So we have a negative, positive, 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 negative, negative, and a positive, negative. So positive, negative, negative, positive. So we have all the combinations for the different types of quadrants. Now we have to make sure that these are actually in the correct spots, though. So the convention here looks like X, then Y, and for X is width, and for Y is height. And this is kind of like a point normal form, right? So let's look for I. So on I, we're going to start at point D, and we're going to take our AX vector, and we're going to go backwards, and then we're going to take our AY vector, and we're going to go forwards. Wait, really? Did I already screw this up? Okay, yeah, so I screwed this up. And now I have to reevaluate my life. Where else did I screw up the coordinate system like that? Well, I think this is the only place where we're, like, intentionally adding and minusing, right? So let's make sure, if we look at where else we're adding and minusing things, so this plus doesn't matter because that's a plus to, these pluses are being used to average, and they're not taking, so we don't have to worry about taking into account, the directionality of things. Okay, so that's the only place where we would have made this mistake. So the problem here is that when we look at this coordinate system, we got to remember that we are in our 3D coordinate space. We are trying to use like a graphical convention. So I kind of have. So this is positive, so this way goes positive X, right? So this is positive x, and then when we go down like this, so when we go down like this, this is the positive positive y. So I kind of flipped things, and it is very intentional that I flip things like this because I want to think of everything in terms of we're just rendering. That's a y. The voxels to me are just three-dimensional tile maps. Tile maps as in pixels of like images, right? So we're trying to use a graphical origin convention here. So positive x is this way, and positive y is this way, right? So if we want to go, this is negative, and so this is, so if we go in this way, right, this is negative x, and yeah, so I'm kind of like, you know, we could probably try to draw it like right here maybe, so that we have some more space, right? But this is our negative y, right? So negative y is this way, right? Because when you're doing math in like math class in school, you would think of this as a positive y, but that is not the convention here because we're going to use a graphical top left origin, right? And because of that, that is flipped around. So you know, we want to make sure we know what our coordinate space is. And, you know, if you are looking at this code assuming one coordinate space and I use another, that's just going to be a world of hurt for everybody. So negative x is over here. Let's just do negative x like that so we can kind of see it decently. And maybe do it like that. Maybe keep it small. I kind of like keeping it small like that so that there's more difference between the negative x and negative y and the positive x. So the negatives and positives, right? The positives can be in capitals and the negatives can be in lowercase, and that can kind of help us kind of see the difference a little bit more easily. So there we go. So that looks good to me. We kind of reestablished, you know, we can make a little note here that this is a raster graphics style top left or origin. I think it's origin or origin. I can't remember. Origin. Let's try just look that up on Google, see if we can find some answers. So origin. Wow, my browser is. I'm just gonna close this because that's not cool. So let's look. Origin is what? Is it O-R-I? Origin. Okay, so it is origin. I always thought that was me making a mistake and just adding extra vowels where they don't belong. Origin. Okay, so yeah, raster graphic style top left origin, right? Because it's the top and it's the left. Okay, so now that we know that, we can double check our math here. And I is going to be negative, right? Yeah, to get to, because we got to go negative on the x and we got to go negative on the y. So we got to change that around. So that was incorrect. Okay, so now we're going to look at j. So j is going to be positive on the x and negative on the y. So that's a plus and a minus. So right now we have a plus plus, but we need a plus and a minus. Plus and a minus, okay? For k, k is down here, so that is a negative on the x and a positive on the y. So neg pos, neg and pos. Okay, so for L, we have positive on the x, positive on the y, so that's just a plus plus. Okay, so now that we have that, let's look at this, and we can do one more kind of like checksum kind of thing. We have a minus minus, and we have a plus plus. And then in the center here, we can see that it's a plus minus and a minus plus. So we have all four combinations of signedness accounted for. We have x's, then y's. X is x and height, y, and, so x and width, y and height. So those variables are correctly paired with each other. Now it seems kind of stupid to kind of like meticulously check this, but I'll tell you that meticulously checking this is going to be a lot less frustrating than trying to debug the weird things that are happening later. So I would say that is now correct. And you have to think about the way we're doing this is this kind of creates a vector of a certain magnitude, right? Of the magnitude HW, and this creates a vector of the magnitude HH, right? Because AX and AY are normalized, and we might want to make absolutely sure that AX and AY are normalized, because that will also create a problem for us. So going back up here, we can see that the end result of AY is normalized, and we can also see that the end result of AX is also normalized. We can see that the braces look balanced, and the braces here, they also look balanced. We can just do a little double checking around there, and that looks good to me. So we've kind of made it down to here, and this stuff here was kind of like already written, but we kind of like just replaced the variables from SDF underscore 009 and replaced them with our new variables. So this used to be A, B, C, and D, and these were like, I believe, A, B, and C, D, but now we've changed it to correspond to our new plane that we're going to be working with. So with this, I and J and K and L, those should be parallel lines. So if we look at I and J, indeed they are parallel lines within our diagram. And the thing is, we really want to trust our diagrams. So I know people are like, oh my god, I hate comments in code because, oh, what if the comment doesn't match the code? Well, if the comment doesn't match the code, then your code is wrong as far as I'm concerned. So by looking at the diagram, we can kind of confirm the validity of the code, which some people would think is completely batshit backwards. But I think that both of them should agree with each other, and you should be able to trust both of them. So, for I and J, those, and K and L, yep, those are parallel. So the idea is that we're going to interpolate between I and J to get a point on this edge. We're going to interpolate between K and L by the same percentage to also get a point on the edge, right? So if we look at this, we can see that we're interpolating with the percentage X on both of these edges, meaning that if we go 80% on IJ, then we'll also be 80% on KL, and then when we want to connect those vertices with a line, we'll get a line that is actually perpendicular, right? And then our next interpolation is going between point IJ, so this is point IJ right here, and point KL would be right here, and we want to interpolate between that to find a point on this line that I'm kind of like drawing in gray right there. So if we look at that, it's going to be IJ to KL and not the other way around, because remember that this is our origin. So at 0%, 0%, we would be at this origin. So IJ should be first. So if we look at this, we see that we have IJ first and KL first, because the percentage Y is going to start at 0 and then move up to 100%. So at 0%, we're going to be at somewhere on this edge for 0% Y, and then at 100% Y will be on this edge, which makes sense because this is the graphical origin that we're working with. So that makes sense to me. What else are we missing? So this is ray world coordinates. So basically we're trying to figure out a point on this surface somewhere, on this plane somewhere, that's going to correspond to a pixel on the screen we're going to render. So we're rendering a screen pixel to this polygon in three-dimensional space. So that looks good. So now what about the ray world normal? So if we look at the ray world normal, we were really lazy about it, and we were just like, all right, just, you know, we're going to shoot straight down. We're going to just top-down view, right? But that is completely incorrect right now. So this right here, this is wrong. And it is wrong because, so we gotta, like, you know, we'll be very obnoxious here. So we'll be like, fix this, right? So we'll go past our column limit. So since I'm very OCD, when I see something that's off the column limit, I immediately want to address it, and I can see fix this. So let's take a look at that and try to fix that. So the ray world normal needs to be something else. And when we were calculating all of those normals earlier, we should probably figure out our z normal, right? Our z normal would be we need something that is perpendicular, right? So, hey. Food? Okay. So, okay, once I figure this out.
It's like Thanksgiving dinner.
Here.
I'm here. I got him.
Okay. So, let's see. So we need another vector. So we got like our AX and our AY vector that we used to recreate that plane, and now we need something perpendicular. Now, the math to create something perpendicular to a plane, you know what, I'm not really good at my math, so let me think about how to just solve this in a more geometric way, because I've been solving all of this in a geometric way rather than a linear algebra way, because I just don't know my linear algebra very well. So maybe I'll appreciate the linear algebra more after I realize how much easier it is to solve all of this stuff when I'm not, you know, painstakingly doing this. So we need to, from point D, we kind of want to shoot into this volume, and we kind of want to, if we average a vector DC, DB, and D, down here is DH, yeah? Yeah, this is DH. So I might want to make a note here that this is H, right? Right, because D and H, right? D and H, right, they're immediately underneath each other, but yeah. So if I take DC, DB, and DH, and I average them all, then I will get like this vector that is going into the that is looking into the volume at kind of like this 45-degree tilt on all axes, right? This like isometric approach, right? It's gonna be like looking on it in an isometric way. So with that, let's take some notes here and be like about what we need. So we could actually just take this diagram. We could just rip parts of it out while we're taking our notes. So we need to average. We need to take vec DC plus vec.
Wash your hands.
Okay.
Who wants water?
No,
or
I was told that this wasn't an obligation to be right up there, and I have stuff I need to finish.
Okay, Jam's not coming out for a bit. At all.
Okay.
Water.
So, let's look at this. So we got vec DC, we got vec DB, and then vec DH. So vec DH, DC, DB, and DH. So that'll get these vectors that are kind of from here. And and the important part is that they're pointing in the correct direction, right? Because we want to, our camera is kind of like, even though our graphical origin is over here, our camera origin is kind of like on the other side across from our graphical origin, if that makes sense. So from here, they're pointing in the correct direction, so that when we average these vectors, it'll point where we need it. So we just need to take these, and then we'll just divide them by 3, right? So divided by 3.0, and then we also need to normalize that. So we'll normalize, right? And then this is, so we have like axis X, axis Y, axis Z. This would be axis Z equals, and we can try to kind of change the formatting to kind of match something similar to what we were doing for the other pieces of code. And so let's do this, and this is a vec3. And let's make sure we didn't put any vec4s accidentally in our code. So looking through this, do we have any vec4s? Because I know I kind of sometimes make that mistake. Nope, so everything is a vec3 here. So going through here, I think it would kind of make sense to put the code in a similar place to where we're defining all of these. So we have AX and AY, and then we need the AZ. So, so this is a comment section, so we don't want to be in the comment section, so we'll just paste that right there. And we'll just say Now these vectors might not actually exist. I just had a very normalized way that I wrote these variable names, so I didn't have to like memorize what the variables were called. I could just make them up on the fly, and since I'm consistent enough, those should be the correct names. So AZ, looking into the voxel volume from a 3/4 isometric direction, right? So that's kind of what we're doing there. And we cannot do that. We cannot add a comment like that because we are... oh, wait, no, we're not inside a comment because if we were inside a comment, then none of this would be code, and then we would have a problem, wouldn't we? So we can add that like that. So AZ. So let's color code these vectors for a second. So let's color code 1, 2, and 3. So make sure that all these vectors exist. So it looks like we've already referenced the cyan and the orange, so it's this yellow that I'm concerned that might not exist. So looking through it, yeah, it does look like we do not actually have that vector. So it's vector DH. So looking at this, okay, so we have HD, but we don't have DH. So with that, we'll just tag this on the bottom, right? So we'll just do vec3 and vec_dh equals normalize, and then we're going from D to H, so H minus D, right? Because remember, we're reading in this direction, D to H. So let's make absolutely sure that all these variable names are correct really quick. So let's highlight all these colors for a second and verify that as well. So you should see the colors on this side and the colors on this side should all be a mirror image of each other. So that is a mirror image, that is a mirror image, that is a mirror image, and that's also a mirror image. So, all right, so D to H. Okay, so we've kind of checked this section of variables multiple times, but since we added another one, it's good to just go back and double check everything again. So with DH, we can now look at that math and make sure that's correct. So let's highlight these colors one more time. And we have 3 things we're adding together. Therefore, to get the average, we got to divide by 3 because we got 3 things this time. And then we also have to normalize it. We don't have to normalize them here because the variables themselves on creation time are normalized. So we don't have to worry about that. So that is good. All 3 colors are represented here. Because when we did our token highlighting here, they just, the corresponding variables were lit up. So we know that these variables are accounted for now. And with that AZ out of the way, we can go back down and we can look at this right here. So this ray world normal, what that is actually is it's just a copy of AZ. That's all it is. It's AZ, right? So it's just that Z axis. So we're not trying to do anything fancy with our camera plane. We are assuming that our camera plane is planar. So if we started to warp our camera plane now, the vector coming off of the camera plane would not always be normal to the camera plane. So we get some, you know, I mean, warping the camera plane in a non-planar way always gets some weird distortion, but I don't know if the distortion would be as pleasing to the eye if we don't, if the normal on the curved surface is not actually normal to that curved surface, right? So because we kind of have hard-coded this normal for every single point on the plane, if we were to do something fancy here and warp the surface of the plane that we are interpolating on, then we would just have some major inconsistencies, right? So even if you're warping space and you're doing these weird warpy filters, right, and you're trying to make some weird effect, just because you're doing something like that doesn't mean that there can't be a lack of consistency, right? So when you're trying to bend and warp things and maybe do things in an unconventional way, you can still screw that up, right? Just because you're trying to do something in an artistic way doesn't mean that it still can't be poorly executed, right? Does that make sense, right? Like just because you're being creative doesn't mean that, oh, anything goes and anything is acceptable. You can still have bad execution with creativity, if that makes any sense. I don't know if that does, because I'm kind of ranting. So that all looks good. Like, it looks good. I'm still kind of paranoid that somewhere I made a mistake. So my goal right now is to have looked at this thoroughly enough that when we take this code and we try to compile it, I do not want to see any errors in this code, right? I want this like if it fails to compile, I don't want none of the failure to compile right now should happen inside this whole section. This whole section for this function, if I see any failure to compile after we've kind of like gone over all of it for like an hour and checking the syntax meticulously, I'm not going to be happy. But you know what? Let's see the merits of this. Like, can I, if I'm super careful and take an hour to look at the code and describe all of the code, can I not make any mistakes? And so I'm going to try to run this, and we're just going to see. Oh, so I guess I can not make any mistakes. Nice. Okay, cool. All right, cool. So so now I have to think about this, and I gotta kind of look at this and be like, well, is that what I expect? And actually, I think that is what I should expect. So if we look at these stripes, it might be kind of hard to understand what we're looking at. But remember that the camera plane that we're positioning in space is kind of centered on that tippity-tip voxel pixel of the voxel volume. So if we look at point D in our code, we see point D right here, point D right here. And if we look at our stripes in our shader, see that little green right there? That green little chunk. Well, I guess maybe I should move my little advertisement for where to find the source code. So let's well, maybe you're just gonna have to trust me here. So inside, I think it's actually inside the O, like because I have this overlay of where to find the source code. Yeah, so it's almost inside that O. So inside, so you can probably see this like O right here. I don't see that on my screen, but there's a little green chunk, and that green chunk is it's green because it's inside of the voxel volume, right? So this so we're still using the camera as a slice plane, right? We're still using the camera as a slice plane. And because of that, I would only expect to see just a little bit of the tippity-tip of the voxel bounding volume. So now you might wonder, well, what's with these, like, what's with this checker pattern, right? Well, originally when we were slicing through this in the previous lecture, we had squares instead of these rotated squares, instead of these diamonds, right? And when you think of an isometric perspective, looking at something in 3/4 isometric perspective, the outline of any cube is going to rotate like this. So we could probably like try to draw that out really quick. So let's try to like, let's get the camera and just show you. here, if we move that camera plane up and down or back and forth, if we like dolly the camera plane, I think that instead of just getting these square shapes, we should see the cross sections kind of shrink and grow. And right now we kind of only see one shape. We just see one shape of one exact size. But I think that as we start to move the camera up and down by dollying it, like so, if you dolly the camera, we should start to see some type of we should start to see the cross sections kind of change shape, because some of these shapes I think will get bigger and some of the shapes will get larger is what I think will happen. So like the gray shapes might get bigger, and the dark checkers might get bigger and the small checkers might get smaller. Now, if both of these shapes are going to change size, then they can no longer tangent each other, right? So they're going to turn into different shapes, right? So, so I think like I think like one of the shapes is probably going to morph into like a hexagon, and the other shape is probably going to like morph into an octagon. So we're going to have like this hexagon-octagon tiling is what I think is going to happen, but I'm not certain about that. So we should try to figure out how are we going to take this camera and dolly it, right? And to dolly the camera, we actually have to take that camera plane and we just got to like move it back and forth. So we got all this math for like figuring that out. And really, to move the camera back and forth, we just have to take this AZ vector, and we just got to take every single point that we calculate, and we just got to like use point normal form to like move it back and move it forward. So this part right here, we can add like a dolly, right? So so for that, we could just do something like, you know. We could do define use animated dolly for debug. We'll set that to 1, and then you know, if so if we have this if greater than or equal to 1. Okay, so then in here, we'll add that animated dolly. So we'll take this and we'll undef this down here. Undef. Maybe line that up nicely. That's a little bit outside of my comfort zone for how close that is to the edge, but it is within my column limit, and I don't give myself a generous amount of space for my column limit. I think right now I'm at a 52 or 56 column limit, and my hard limit is 64. So I can use up every last character because I have a very stringent limit. Okay, so for this, how are we going to do that? So we're just going to take these, and we're going to use point normal form to just kind of like move it back and forth. So we'll do like plus equals, and we'll just take the AZ times dolly amount, right? And then we'll just duplicate that 4 times, and then we'll just take these, we'll paste them into these spots. Okay, I, K, right? And we know that AZ right here is perpendicular to the plane. So since AZ is perpendicular to the plane, we can effectively move that plane back and forth, or into and out of the geometry, zooming in, zooming out, right, by physically moving the plane along its normal, right? And this is kind of hacky because we're kind of like we're doing 4 multiplications, but let's just try that out. And obviously we need a variable for dolly amount. So let's say that like I really don't know what a good amount for this is. Well, we could try something like if we wanted to be like really precise about this, we could take the diagonal distance of our voxel volume, but I really don't want to, so I think I just want to take, say, like, the largest value here. So we got NTX, NTY, but the other thing is I don't really want to total pixels, so TPX, TPY, TPZ. I think we'll just take all three of those and we'll find the max, and that'll be our dolly, our maximum dolly amount. So, so within our math here, what we'll do is we'll say F32 max dolly equals, and we'll do max. Do we have a max that uses all three values, or did we get rid of that? Let's just do max. Let's not worry about that. We'll do max, and we'll do total pixels x, comma, max, TPY, TPZ. The other problem here is that that's not going to work because these are they are integers, and so I am pretty sure that the max function will not work with we got to do this. The max function isn't going to work with integers. I know it's not overloaded like that. I don't know why, but most of the functions are really not overloaded for integers. I don't know why that is, what the rationale for that is. So this kind of is going to look really ugly as hell. So let's just do it. Let's not worry too much about how ugly it is. Let's just write it out and then maybe figure out a way to like make it look a little bit nicer after we've kind of like figured out the logic. So max, and then we can let's just use this comma to separate the two terms we're taking the max of, and you know, we could have like these line up, so that's nice there, and then we could also do you know, we could really abuse how much space we're using here on the vertical and just like really make it kind of like easier to follow. So I think is that good. So we got the max, and the max is going to take this parameter, and then it's also taking this parameter. So do we want it lined up like that, or do we want to do it more like that? I think having this comma here makes it a little bit easier, because then we see max, parameter, comma, another parameter. We could also indent a little bit more, and then we could do that, right? So it's just make it very obvious, right? So I think I'm okay with that. I mean, it's a little bit wonky. Maybe it's probably not the way you would choose to do it, but we got x, y, and z. This is why I have a function for, let me make sure I don't have a max. Like, I'm going to just search for the word max and see if, I know I wrote a utility function in another piece of code that kind of like takes the max of three values, but it looks like I don't have such a max function anywhere else, because I only see, hold on. It's telling me max can't be found, but let's just remove these. Oh, wraparound is missing. That's what I'm doing wrong. So we'll match the case, and let's see. I'm surprised I don't have the word max in more places. Okay, so that's good. So we got this max dolly, and then this dolly amount, and then to get the dolly amount, we'll just do F32 dolly amount equals I time multiplied by max dolly. Actually, no. We'll do cos I time and that will get a value that kind of like fluctuates between -1 and 1, right? And we can then use that as a scalar on max dolly, right? So then we can go back and forth the maximum amount when we're dollying. Okay, so now that we have that, we can double check this math, make sure that everything is in order and everything looks correct. So float 32s. The max function needs to be used with float 32, and that's why we wrapped tile pixels x, y, and z within float 32 constructors. This is also a float 32. Cos is a float 32 multiplied by max dolly. That looks good. So is this correct? So we have this so this is a vec3, and we're taking az, which is a vec3, and we're multiplying this normal vector by the dolly amount. And that also looks correct to me. So I think that we've looked at this carefully enough that I'm hoping that I didn't make any mistakes, because I'm trying really hard to explain things concisely enough, or not concisely enough, explain in enough detail and check thoroughly enough that when I run this, I don't want to see any problems. Yeah, no problems. Oh my god, that's not what I expected at all, but okay. So that is something, alright. So we can kind of see that as we slice into oh, you know what? It's the reason we're not seeing any hexagon kind of shapes, I think might be because it almost looks like my camera is just rotated and looking straight down. It looks like my math might not be correct. Or, hold on, let's try to pause it. Oh, no, I think that there's an optical illusion happening here where it looks like, as we see the green sections, it kind of looks like this optical illusion where we're kind of like looking through like a crack. It kind of looks like we're looking through this crack in a fence. It almost looks like we're looking through a crack in a fence. Like there's this fence that's like moving up and down, and we're looking through the crack, and we can see the entire voxel volume from the top down, and it's like slightly rotated. That's what it appears to be, but I'm pretty sure that's not what we're actually looking at, because I know this is a cross section, and I know we're moving up and down through that cross section, so that wouldn't make any sense. So we do need to think about, well, why would the I just want to have some fun here, but you know, is that correct? Like, if we take a orthographic 3/4 view of a cube, does it actually end up just looking like a square? Like, if we look at it from that perspective, does it end up being a square? That doesn't sound right to me. And I need, like, I got a whole bunch of like square things around me, so maybe I can start to like. No, I mean hexagon all the way, man. What about if I tilt it, right? Nope, because once I... No, because if we tilt it, yeah, so this, I don't think this is correct. I don't think what I'm looking at is correct. I think some of my math has to be wrong somewhere, and I'm hoping that it's just that the construction of my camera plane is incorrect and not something else. But let's just have some fun. Let's take like I and j, and let's just minus equal to get the camera plane to kind of like move a little bit differently and kind of see what that looks like and kind of observe the effect and kind of just see what it looks like and have some fun here. That's kind of trippy. And that makes sense because you see how it flips? That would be because... That's because, remember, our camera normal is not... our camera normal is hard-coded, so as we're warping and distorting the camera plane by, like, giving it this tilt, the normal doesn't change, and so eventually the normal ends up pointing on the other side of the plane, and that's why we're seeing the image flip. That's still kind of crazy that we don't see. I'm still expecting to see some type of like hexagonal values or hexagonal things. Okay, so let's just mess around a little bit more and kind of see what we see, and kind of observe the effects of what's happening, and you know, see if it makes sense to us. You know, oh, that's kind of fun. Yeah, so we got a problem on our hands, and we got to figure it out. So... Oh, wait a second. Wait. No. Okay, so my thought is, as I'm kind of looking at this, that maybe the mistake I'm making when I'm trying to interpret what I'm visually looking at, so let's just put this back to what it should normally be and give this a run for a second. Okay, so when we look at this, and we're dollying, can we... Let's get rid of the dolly for a second. So let's change that to 0. And we'll save that. Control A. Okay, let's get rid of the animation for a second. Okay, so perhaps if we connect, can we connect these different colored regions and end up getting some type of hexagonal shape? And the answer to that actually is yes. Yeah. Okay, so I thought, I was like, where are my hexagons? I don't see any hexagons. And they were in front of me the whole time. So, so when you're looking at this, these light checkers represent one layer on the Z axis, one layer on the Z plane of voxels, and this darker checker is another layer on the Z plane, plane of voxels. So these are different layers of voxels. So I'm looking at these shapes, and I'm kind of like looking at this little green tip, and I'm looking at this, I'm looking at that, I'm like, oh, that's a square. That's a square. Where the heck are my hexagons? I should have some hexagons, because we're looking at this in a 3/4 view, and so now all our squares should be turning into hexagons. Well, they are, because I'm just kind of like connecting the shapes, because what I see here is, you know, it looks kind of like there's this checkerboard pattern, and then there's just like a dark rectangular overlay over parts of like a light gray checkerboard, but that's not what we're looking at all. So if you see this this section where my mouse is, this I'm pretty sure that's a hexagon, right? So one side here, 1, 2, 3, 4, 5, 6. Yeah, hexagon. We got a hexagon. So right here we got a triangle, and then over here we got 1, 2, 3, 4, 5. So we got a irregular pentagram. But yeah, so okay, so we actually have the shapes that I was expecting. So if we're gonna make it dolly again, because I'm gonna guess that when we dolly in and out, we're gonna get some, at some points in time, we should have something that's a more so we also have to remember that these are cross sections. These are cross sections, so we're not going to see exactly the type of hexagon you would expect. We're like we might not be able to expect a regular hexagon from these cross sections, because they're cross sections. This is not a camera view yet. This is using the camera plane to kind of like cut through the geometry and just analyze what the cross section looks like. And that is probably what's throwing me off a little bit. So it still looks kind of weird to me, but this could actually be what it needs to look like. And the only real way to figure that out is I could open up some OpenSCAD and just take a cube and try to slice into it with another volume that is correctly oriented, and I could make sure that that shape looks correct, right? So I think that is actually what I'm going to do. So I'm going to go upstairs, get some food, but yeah, because I'm at a good stopping point here, but I think I need to cut into, just get some OpenSCAD, cut into a volume, and kind of see if everything kind of like makes sense, or that make, you know, because I can't really visualize it. I can't really visualize what the cross-section of a cube is. We could try to check online, just see if we can find a cube cross-section. Like maybe there's already some visuals. Cube cross-sectional cut, right? We just want to figure out what a cross-section of a cube looks like. And so it looks like on Khan Academy, I just found like a video on ways to cut a cube. And the little preview image was actually cut from the where I want to cut it at. So, okay, yeah, so when we're looking at, so here's our isometric, so we're just looking at the preview of this video. And we can see that from the isometric view, when we're cutting into the cube with a slice plane that is oriented how we oriented our camera plane, that we're getting triangles. That we should be getting triangles. Now, if we go deeper, do we end up getting a different shape? And the answer would be yes, right? Because we cut, as we go deeper and deeper, eventually this triangle is going to hit all of these vertices, and we're going to have a pretty large triangle. But after that, the triangle is going to turn into something else, right? The vertices, for every single vertice where this triangle is, for every single vertice on this triangle, once we get past these vertices on the cube, the vertices on the triangle are going to split, right? So we have 3 sides, and it's going to turn into 6 sides, but you're going to get like these irregular triangles. So if I look at my screen here, you know, I see triangles, which makes sense. Do I see anything where it looks kind of like a triangle that's kind of been split? Yeah, I mean, kinda. Like, this is a triangle, and this vertice has been split, but not this vertice. So that is still kind of concerning, I guess, where I'm like, I'm still not quite sure if what I'm looking at is correct. But now that I kind of see this, I think I might just watch this video later to make sure that I have a better visual reasoning in my head of how these shapes are kind of sliced. because I am kind of like slicing space, so that would probably be good for me to understand that. So I'm gonna stop recording, and then I'm gonna see if I can get some food, or if I've been outcasted from the dinner table or not. We'll just see where that goes. So yeah.